All right. So we looked at directed probabilistic graphical models that can do things that fundamentally things like convolutional neural networks cannot. And we looked at an algorithm, variable elimination, that allowed us to do inference, exact inference in a very general setting. And today and on Monday next week, I want to give you two concrete examples for important directed graphical models. And the example I want to give today is called hidden Markov models. And it is useful, for example, in robot localization and many other things. For many years, by the way, it was used for speech recognition quite successfully. But in that domain, it has been superseded by neural networks in the meantime. So I'll start with a sketch. This is from this book, which you see here. Slides are in the public document by Sebastian Thun, Wolfram Burgert, and Dieter Fox. Sebastian Thun, if you remember, was also head of the team that won was it the first or second DARPA challenge? So the first time that an autonomous vehicle managed to, really get anywhere in desert environment. And nowadays he's busy with a company that's trying to build flying motorcycles. And hopefully we can buy one soon. So that's a picture from his book. And first we look at the picture, look at the problem qualitatively, and then we will do the math. All right, so we have this pretty robot, and let's assume that the robot tries to figure out where it is. That's always a useful thing to do for a start before you want to take over the world, to know where you are. This robot has a sensor, and now it has just been booted, and it has no idea where it is. Yeah, so you see this spatial axis X, and you see on the vertical axis its belief of where it is in space, and initially this belief is uniform. It has no idea where it is. Let's also assume here that the robot does have a map of the environment. It just doesn't know where it is. Yeah? So it next uses its single sensor. This could be a depth sensor, or maybe it's a color sensor. And this sensor tells the robot that actually it's close to a door. So we see here the probability of the measurement z given possible coordinates x, and this measurement is most compatible with the map if the robot is either here or there or there. But we don't trust the sensor fully and completely, and hence you see that elsewhere actually the probability is not zero, it's just much lower. All right, now how should the robot determine in front of which of the three doors it is standing? It can now move a few steps. So it has taken its wheels and decided to move a little bit to the right. And you see that its belief, so previously it thought I'm either here or there. After moving to the right, this belief has been updated. Yeah? So now the robot thinks it's either here or there or there. If you look closely, the robot, based on past experience, knows that its measurements are not, or its mechanics are not completely accurate. So if in fact it wants to move 2 meters to the right, then in practice it may move 2 meters and 2 centimeters, or just 1.95 meters. So it's not quite sure, or there's an added source of uncertainty. So if you look at this belief, yes, the peaks have shifted to the right, but they have also become a little bit broader. So here it was fairly peaky, and now the peaks have become a little bit wider. Now at this point, the robot can perform a new measurement. This new measurement you see down here, in fact, the measurement tells it that it's close to one of the doors. So just based on the measurement alone, the robot would think, well, I'm here or there or there. But now we also have this prior belief. Now we can multiply the prior belief with this new likelihood, and we get an updated belief, which you see down there. So if you multiply this distribution here with that distribution, you get the one down there. And now we get a nice sharp peak around this door and smaller residual peaks and a little bit of uniform distribution elsewhere. So now the robot is actually pretty sure that it's in front of this second door. And then it can move further to the right and start take over the world. Good. So that's what happens qualitatively. And we will now look at the math. So in the equations that follow, I will use these equalities that you already know. Yeah? I've just numbered them here so that later we can more easily see which one was being used at a particular point in time. This looks very messy. Good. All right, so the first one is the joint probability of A and B can be written as probability of A given B times probability of B, or vice versa. The second one was Bayes' theorem. Probability of A given B is the same as B given A times A divided by probability of B. And we've used in variable elimination this marginalizing out of variables that we were not interested in. And we spent half of Monday this week to talk about this following important equation. So in a directed probabilistic graphical model, we have that the joint probability of n random variables is given by a product of the probability of each random variable given its parents. All right, this was the convention that we used last time. This is the equation that we have in mind when we draw a directed probabilistic graphical model. Good. Example. If you look for robot localization, you find plenty of these videos. So cats and these robots get along really well. I also have one of these at home. I'll show you a movie, maybe a little later. Yeah. For now, let's devise a graphical model. So what we need is a state space model, in this case for self-localization. And we will distinguish between a state. So let's say we leave a little bit space up there. Yeah. We have the locations, which are a hidden variable. I'm calling it X today. And we're interested in the locations at all times, from the first time step to capital T is the final time step. Then we will also have sensor readings. You saw that the robot must be able to make some measurements in order to find out where it is. I'm calling them R for readings. R1 up to RT. And the robot will also perform actions such as walking to the right, which I assume are observable. All right, now for the locations, I already said the model is called hidden Markov model, so we make this Markovian assumption that where we are now, let's say at x2, only depends on the previous state, where were we in the time step before, and on the action that we've taken since. So we have variable action 2. And I'm again going to shade this box to say that this is observed. An observed random variable. Now, we also have these sensor readings. And the sensor readings, they are, of course, determined by where we are. So we would have here a sensor reading R2. They're also dependent on the world that we live in. So I could have an extra random variable which I call world. Don't copy it. We say this world is observed because we have a map, but I'm omitting this for now. Okay. So we have the sensor reading R2, and then we can go on. So let's say at x3, the probability of where we are at x3 for sure will depend on any action that we have taken, again assumed to be observed. It will depend on where we were before. Do you think it will also depend on this sensor reading or not? So x is where we are, R is what we have measured. Not really, huh? So where we are depends on where we were before, but not what we measured before. So there's no, I'm trying to avoid the word causal, but there's no relation between, there's no immediate relation between what we have measured before and where we are now. The only thing that matters is where we were before. Okay, and by the same reasoning, we can now extend this plot. It goes on and on. And for the first state, let's say we also have a reading R1. And perhaps we already took an action A1 that took us to this first state. All right. So the headline I chose was a state space model. And whenever you see somebody draw like this, then you know that it's a state space model. So often people omit the variable names, but in the literature you will frequently see this fundamental pattern that we have just drawn, where the things on the bottom are observed, and the thing on top are latent variables that we're trying to estimate. And whenever you see something like that, this is called a state space model. And you can find literally thousands and thousands of papers that have this figure, and then you find tens of thousands of more papers that do the same thing but don't have this figure. Especially the papers that appeared before this framework of graphical models became widely known, people were developing that kind of model, but they didn't have this nice way of summarizing it. All right, so now this is a directed graphical model, and we can go about writing out what are the joint probabilities of these random variables. So we'll start by giving this joint distribution of all locations, all actions, and all readings. And well, now given what we've learned about probabilistic graphical models, maybe you don't want to copy it, I'll write it explicitly once and then give you the more generic formula. Okay, so for all the things that we see here, we would have the probability of x3, and x3 depends on its parents a3 and x2. And we have the probability of R3 given x3. This was for the thing on the right-hand side. Then we have the probability of x2, that depends on a2 and x1, and the probability of R2 given x2. And finally, we have the probability of x1 given a1 and nothing else. And the probability of R1 given x1 and the probability of a1. Okay, this was explicit. And if I write it a little more generically, we have the product over all times from 1 to capital T. We always have this probability of xt given at and xt minus 1 times the probability of rt given xt times, I have forgotten two terms here. I have forgotten here the probability of A3, and I've forgotten there the probability of A2. So times the probability of AT. And then we need, we have this corner case, we need to define what we mean when t equals 1. So we define that the probability of x1 given a1 and x0 is just the probability of x1 given a1. Now, when the robot, runs for a long time, this is of course a huge graph, and we have very many random variables, and the usual comments apply that this factored representation is much more economic in terms of storage, in terms of computation, than writing out the full joint. Okay, now what do we want to compute here? So, wanted. There are two typical questions that you can ask. You may be interested in the probability of xt given all actions from the very first to the last, and all sensor readings from the first to the last. Yeah, so note I write a small t here, that's the present time, and 1 to t means all times, even the future ones, when I have a recording. And This amounts to the question, where was I, retrospectively you can ask, where was I at time t? Or you can condition only on past observations and actions. So we can be interested in this quantity. Amounting to the question, where am I currently? Yeah, given the past measurements. And in more abstract terms, the first problem is also known as offline estimation, because you can only do it after the fact. Or especially in the Kalman filter literature, this is called smoothing. Or in the second case, we have an online estimation, which in the Kalman literature in particular is known as filtering. So the first equation, or the first kind of problem, you can only solve at the end. Yeah? So let's say you have a recording of things the robot did and things it measured, and then after the fact you try to find out where was it at some time small t. And the second setting is more interesting for real-time applications. You try to find out where am I now, given all my actions to date and given all my measurements up to date. All right, so we will now look at this second thing, and using, I've numbered the equations above. Using this first relation, I can rewrite this as the joint, the probability of xt and a 1 to t and r 1 to small t divided by the marginal. This is generally true, except that here the denominator, it's important to get correctly normalized probabilities out, but it does not depend on the location. And if I'm interested in where am I, then currently I'm not primarily interested in this normalization, and hence we will ignore it for now. And we concentrate on this first term. Yep.
What exactly is the equal sign referring to? So what is equal to?
It is equal to this. All right, sorry, I know you cannot do this on paper. I'll just copy it here. All right. So because the denominator is uninteresting, we will concentrate on this numerator for now. So I'm copying it again. The probability of xt and a 1 to t and r 1 to t. I can always write this. So we will now want to do variable elimination. Yeah? So and we want to end up with a recursive expression. So I will start by writing this as marginalizing out the previous state. So we have the probability of x t minus 1, xt, a 1 to t, and r 1 to t. And we marginalize out t minus 1. And this was from the numbered equations above. This was equation number 3, which holds in general. All right, and we will now, our goal will be to do this recursively, but for now, let's factorize this probability in the kernel of the integral as far as we can. So first we want to separate the present from the past. So I will write the reading at time t, given all the other variables, xt and xt minus 1, and all actions up to time t, and all sensor readings from 1 up to t minus 1. Times the things that I have just conditioned on. Now I need the joint, xt minus 1, a from 1 to t, and r from 1 to t minus 1. Okay, so what have I done? I have taken this joint probability here, and I've pulled out one of them and conditioned on the others, and then I need the joint of the others, and the joint of the others I have factorized again in xt given those, and then times the probability of those. Yeah, so it was using this equation number 1 twice. Okay. So 1 has been used and 1 has been used again. All right. Now let's look at this probability here. The conditional probability of the sensor reading at times t, given all of these other things. Let's compare this to the graphical model that we have drawn. So I'm scrolling up to the graphical model. I'm putting the equation here so just we can look at it at the same time. So let's say this reading at time 3. Let's say this one here. We are interested in the conditional probability of that given xt. That would be that. And then given several other variables. But we can see that in this particular directed graphical model, RT given xt is conditionally independent of all the others. So these I can simply omit. Okay? Does it make sense? RT depends only on xt and not on the rest here. Which is why, further down, I'm replacing this first term just by the probability of RT given xt. And I've used this equation 4, the fundamental equation of how a probability factorizes in a directed graphical model. Then, for the same reason, we can simplify this term here. We can again look at it next to our graphical model. Excuse me. The probability of xt given xt minus 1, probability, let's say, of x3 given x2. And then we have these further conditioners here, all the actions and all the sensor readings. And the only one that matters for x3 is this action AT. This one matters, but the rest does not. So I can omit this, and I can omit the actions from 1 up to t minus 1. All right. So down here, I'm now replacing this term by just the probability of xt given xt minus 1 and given the action at time t. And the final term, this is now here a joint probability, and if we look what it contains, all the hidden states, all the latent states up to t minus 1, all the readings up to t minus 1, and in addition, the action at time t. Yeah? So in terms of the plot, it is the joint probability of this and of that. And these two I can simply factorize. So I can write this final term as the probability of x t minus 1, a 1 up to t minus 1, the readings up to t minus 1, and the action at time t. Now the reason to have done this is because people spend a long time figuring out these equations. Yeah? So we are only, I'm not asking you to invent them. We're only understanding the scheme that people spend a long time developing. Now the nice thing is that what we have here is of the same shape as what we had there, and will form the basis for our recursion. Yeah? But before we write it fully, we can pull out of the integral the things that don't depend on the integral. So the integral goes over xt minus 1. So the first term does not depend on it. So I'm pulling it out, the probability of RT given xt. And I'm copying the second term. The third term. So these are the only terms that depend on xt minus 1 at all, and the others I have pulled out of the integral. All right, and in this state space model literature, this term here that we are trying to solve for is called the belief. It's the belief of where we are, alpha of xt for short. I'm omitting here the actions and the readings because after having observed them, they are constants. Yeah, so the only variable in here is xt. And the new belief depends on the old belief that we see here. This was the old belief, alpha of xt minus 1. All right. Now, I would like you to try and say in words what these other two terms are. So we have, let's start with this one maybe. The probability of being at location xt, given that we were at a location xt minus 1, and given some action that we have performed. So I'm taking you back to the diagram that we had here. So it was the step from here to there. We are interested in the probability of xt given our distribution over states that we think we might have been in at times t minus 1 and some action that we have taken. So the robot moved to the right. Between here and here it moved to the right, so the distribution has shifted to the right, and we observe this broadening of the peaks. So in words, what is this? What is this quantity here? Yeah?
Yeah, given that we were at a position xt minus 1, where does the action t, so I don't know, maybe rotate the wheels around once, where does it move us?
Exactly.
That's why they're broadening, because the movement isn't exactly 1 centimeter, but maybe 1.1 or 1.9. And it's also, of course, dependent on where you were before, because if you move 1 centimeter to the right, it depends on where you were before.
Exactly. Yeah, very good. And for applications like this one, this would be called the motion model. Because as you have just described, it's a model of, how does our position change as we do something. In this case, the action is a movement or an intended movement. And we will see this again on Monday next week when we talk about the Kalman filter. Here, the hidden state was just where are we? Usually when we apply the Kalman filter, then the hidden state is where are we currently and what is our velocity? And based on where we are and what is our velocity, and given any actions like putting on the braking boosters or not switching on the braking boosters, we can predict where we will be at the next time step. So for a physical model like that, that's why it would be called a motion model. Yeah, so this is a mechanistic model with a noise component telling us how can we predict the next state given the current state and the action. Yeah, so for our application here, this would be the motion model. All right, and then we have another model which tells us how compatible is a given measurement with a particular position. So going back to our sketch, here I have called this the probability of RT given XT. They've called it Z given X. So let's say maybe the robot has a color sensor, and this color sensor says that I see a dark brown that's more a door color than a brick color, or perhaps the sensor says I see a surface with a depression. So this depth sensor would tell us that given the map, we're more likely close to a door here than close to the brick wall. So this term here asks, I have some measurement, which is not shown in the picture, and how likely is this measurement given any of my positions x? Yeah, so if the robot sees dark brown, then at this position x, this measurement would have a low likelihood. Not zero, because I might always have noise or something, or a measurement error. But for this position x also, and for this position x also, the likelihood of my observation that I've made is low. For these positions, however, the likelihood of my observation is much higher. So altogether, what I have here is a measurement model. So, a measurement model. And what we find, what we have here altogether is something. If we look at what it depends on, this depends on past actions, on past measurements or sensor readings, and it depends on past state also. But it does not depend on the new reading. So, in other words, this is the best possible prediction of where I can be. So this is a prediction. And if I don't have a new measurement, then the prediction is the best thing I have. But if, in addition, I do have a measurement, then I can now combine my prediction with this measurement model or with this likelihood. And in this literature and in Kalman filters, this would be called a correction step. So altogether, this is called a predictor-corrector algorithm. A predictor-corrector algorithm. In our case, to update the belief of where I am, given my past belief, and given my new measurement and the motion model. All right, here it's the predictor-corrector algorithm. But if you now do this forward in time, then it turns out to be just an instance of variable elimination. We start, if we do this forward in time, we start by, at the very first time instance, we have no prior belief, but we have a likelihood. And that has determined, if you remember the sketch further up, that was our initial estimate or our initial belief where the robot could be. Then this initial belief was combined with, we performed an action, was combined with the motion model. And then the variable that we no longer care about, x1, was eliminated, was integrated out. And this was multiplied with the second factor that encodes our new measurement to get our new belief, etc. Yeah? So what we have here altogether is just an instance of variable elimination. And in variable elimination, as I have said on Monday, and as you will see in the exercises, the elimination order really matters. The elimination order is arbitrary, and we could start eliminating variables not at x1, but we could have started somewhere in the middle between the beginning and the present time. But this would have resulted in more cumbersome computations. And here, by eliminating variables one at a time, we are passing messages from the ancient past to the present. And this is why this kind of algorithm is also called message passing. All right, let's look at the picture again. It's the very same picture. Just we look at it again in the light of what we've just seen. Yeah? So on the top, the initial belief, which was here assumed to be uniform, we have no idea where we are. Then we used this measurement model, multiplied it with the initial belief, which was uniform, to get an updated belief. Then an action is performed. So from here to there we have this action. And we apply our motion model. And we can now integrate out this previous state variable, x1, to get our updated estimate of where we are. And then we multiply this with the likelihood obtained from the next measurement to get the updated belief here. Yeah, so the pictures are an iteration of this equation here. I want to give you an example, what if we don't perform new measurements? The example is again taken from this book here. We start at some initial location and perform an action. The action has here been to walk 1 meter to the right. Thanks to the, so we get a, thanks to our motion model, we now get a little bit of uncertainty here of where we are precisely. Then comes another action. It adds to the uncertainty, so we convolve the old with the new uncertainty. We get another action, walk another meter to the right. And so far, by the way, you see that this distribution here it's symmetric with respect to the direction in which we move. Now at this point, the robot is told to move left or turn by 90 degrees and to walk forward by another meter. And now this particular robot for which this motion model holds is similar to these vacuum cleaners. So it has a wheel on this side, it has a wheel on that side, and then two tiny supporting free-floating wheels. So this thing can turn by 90 degrees by this wheel moving a little bit in that direction and that wheel moving a little bit in this direction. And you see that the motion model here of this robot has been characterized. And you see that this now induces a distribution which is no longer fully symmetric with regard to the direction of movement, but this is now a little bit skewed. Okay, this is due to the way this robot was constructed. And then it walks forward by another step, and it walks forward by another step. It's told to turn left by 90 degrees, and it goes on and on. And these measurements or these uncertainties over time, they add up. So we had a very precise starting location, and then we have a very diffuse idea of where we are after these 10 steps. So now it would be a really good time to make a new measurement. And then, of course, we have some measurement uncertainty, but perhaps our measurement tells us that we are here, plus, now I would need to sketch, the uncertainty of this measurement, and then we multiply the belief of where we are with the likelihood of this measurement to get an updated belief which would tell us that maybe we now think we are here, and then we take it from there. I want to say one more thing about how to represent these beliefs. In all of the sketches earlier, the book plotted these nice continuous curves. In practice, in hidden Markov models, we have a discrete hidden state. And so how can we discretize this? The easiest way is to use a grid or a histogram. So if you look closely, we now have many small bins that tell us where we could be. And we simply use that histogram as a representation. This has certain limits when the robot has to move over very big spaces, or when the robot moves in 3 dimensions, simply because the histogram at some point ends up having very many bins. An alternative is to represent the distribution in terms of particles. So here, the distribution is represented by grains or particles that have here been sampled in the first picture from the uniform distribution. Then when a measurement is being made, the particles are reweighted. And you see here in terms of these amplitudes, what is the estimated new weight of each particle. And then comes a resampling step, because we want to use many particles in areas of high probability, and we don't want to waste particles in areas where we anyway think the robot probably is not. So if we had n particles, these n particles can now be resampled from the old ones. And in this resampling step, the original positions plus or minus a little bit of jitter are being used. So after the motion model, you see the things here have moved to the right, but at the same time, the particles have been resampled. So we have a large density here and a small density over there, and so on. But overall, overall, in a hidden Markov model, what we have is a state space model with a discrete latent or hidden state. We make no statement about the measurements. In fact, the measurements, they can also be discrete or they can be continuous. So in the example that you see here, this measurement model is a continuous one, even though the state itself is discrete. So in this particular example here, this would be continuous, and this thing, the hidden state here, would be discrete. All right. Now that would be a good point in time to ask any questions that you may have. Yeah?
Can we apply a similar scheme, for example, for a computer mouse, where we actually don't know the action that was performed, but get it also from the measurements? Is there something similar we can do?
The question was for the computer mouse. You mean the pointing device?
Yeah, exactly.
Well, usually we don't care where exactly the mouse is on the mouse pad.
Yeah, but we care for a relative motion, right?
So we care for relative motion, you say. I mean, overall, this is a strategy that can be used for denoising, but what would be the hidden state here? The hidden state would be the user intention, or what would be the hidden state?
I think just have the position. For example, I want to have the mouse on the mouse pad, and if I move it, I want to have the cursor move on the screen. So I still need the position, right?
So I think a computer mouse is probably not the best example of where this would be used.
Yeah, but I would be interested in a system where we don't know which action was performed on the system, but we have to get the action from the measurement. Is there something similar we can do?
Yes. So you're talking about actions. If we have so here I had assumed that the actions are observed, but indeed we can also try and infer the actions. Yeah? So we could have some of these action bullets not hashed, and given the sensor readings and given our motion model, try and figure out what the action has been.
Okay, so this works similarly.
Yes, that works. The principle is the same. More questions? Yeah.
Let's see the four fundamental theories again.
The four equations that we've been using were those. Yeah.
Isn't it more realistic to assume that our actions depend on the previous measurement?
The question is it not realistic to assume that the actions depend on the measurements? Yes, very much so. And here I have simplified things by saying, the actions, they just, fell from the heavens and in addition were observed. Yeah. So if we take this vacuum cleaning example, we have something, let me call it the mission, That's the thing, let's say, the robot wants to accomplish. Let's assume that the mission is actually observed. So I know the mission. For example, I want my robot to creep into all corners of the dirty apartment. And now the robot would, well, first try and localize itself, and then it would use its current best estimate of where it is in conjunction with its mission to find out what is the next action. Yeah, so I could complete my my graph, something like that. And here I've completely omitted all this aspect of what is a mission, and or we can also more generally have also rewards associated with certain actions. This is not represented here. So in fact, when we have a system where we want to maximize a reward, so the reward could be, let's say, the amount of dirt collected or something, then I need decision diagrams, a small extension of graphical models where the system has the possibility to figure out what action is going to give it its highest expected reward. All right, in addition, now this vacuum cleaning, in fact, is a harder problem than I've shown here, because usually when you buy such a vacuum cleaner, it does not have the map of your home built in. So it needs to create the map in the first place. And this is a harder problem known as SLAM, or self-localization and mapping. And here, earlier I had said that, well, we really have this map, which is observed, and then the readings together with the map inform on, or the sensor reading actually depends on the map, and it depends on the state that I am in. And in SLAM, this map is an unobserved random variable. And moreover, you see it's a random variable. It's unobserved, but it affects all of those sensor readings. And if you now look at the graph, it is no longer a tree, but it now has loops. Yeah, so if I delete this, here, topographically speaking, my directed graphical model is a tree. And by introducing these, so a tree is a graph with no loops. And by introducing this map, I have introduced loops into the system. And this means that if I run a variable elimination on a system with loops, then I create factors with many arguments. Here in this example on the tree, variable elimination was so easy. Yeah? So whenever I eliminated one variable after the other, I obtained a new factor that depended on just one variable. It was very easy to marginalize over. When I have loops, variable elimination still works, but I obtain huge factors. And this is why SLAM is a much harder problem, so hard, in fact, that a lot of approximations are being used in making it run. But still, these house cleaning robots have a pretty good approximation built in.